Hello and welcome to another Standard Motor Products Power Hour. The topic for today is internal airflow, meaning cabin airflow or in-dash airflow. When a customer complains about poor air conditioning or heater performance, it can be challenging to determine the exact source of the problem. There are many components in the HVAC case that could directly or indirectly affect airflow volume, temperature, and direction. So in this session, we want to provide some diagnostic and service tips to help you get better diagnostic direction on in-dash airflow issues. My name is Peter McArdle. I will be your host for today's session, and let's get underway. So here on my left, I've got a series of failed blower motor resistor circuit components. You can see here I've got an actual blower motor resistor. It's got a burned terminal here. Here I've got a conventional pigtail resistor pigtail connector, and you can see it's got a terminal here. Here I've got a blower motor, and you can see that the segments are pretty badly worn and burned, and a series of issues that can sometimes lead to repeat blower motor resistor failure, poor blower motor performance, and oftentimes it can be difficult to figure out just exactly which of these components might be the issue. Or for example, why a blower motor resistor keeps failing, or why you think the airflow is not as much as it should be, the volume is not as much as it should be, or the blower motor is not rotating as fast as it could be. And so in this session, we have a live demonstration set up down the road here, where we're going to use an oscilloscope to look at blower motor current patterns, to look deeper, to give us deeper insight into blower motor circuit issues using an oscilloscope makes it quite easy, or very easy, and can give us deep insight into what's going on without having to take things apart. So let's get underway with our session here. So, first thing, of course, you want to figure out, is it actually an airflow problem? Is the problem really in the dash? We're going to look at blower motor and cabin air filter service, some basic tips. Air door actuators, the little doors, the motors that turn the air doors back and forth in the dash, we're going to look at those. Some HVAC service tips, you're taking the HVAC case apart, or you're doing something inside the HVAC case, some things to watch out for. And we won't spend a lot of time, but we will give some tips on heater system diagnosis as well. So just before we move on here, don't forget 4s.com. There are a lot of great resources there at 4s.com. You can look up by year, make, model, and look up all the air conditioning related parts for a particular vehicle. Also of particular useful, if you look up lubrication for a particular year, make, model, and type of compressor, it will tell, for that particular vehicle, it will tell you the type of oil, the viscosity of oil, and also the amount of refrigerant and oil. So again, a useful tip, useful resource. There's also another tab there called Technicians Resources, and there's lots of really good technical information here. How to do a maximum heat load temperature or a differential temperature test. Lots of really good technical, air conditioning related technical information here. And don't forget, there's also over on the right hand side, there's a link to our YouTube channel. And going there are literally hundreds of videos available. And many of them have to do with the air conditioning related issues like dye leak checking, electronic and dye, leak checking, both electronic and dye techniques, charge accuracy, blower motor circuit diagnosis, and so on. So don't forget to visit that. Now, again, we have a customers come in the shop and they have a complaint about, an air conditioning or heating system related complaint. And here are some of the questions that I always have in the back of my mind as I approach a problem. Is the airflow volume enough? Is it hot enough? Is it cold enough? Is it coming from the desired outlet? Is there a humidity concern? For example, in the winter when we go to defog the windshield, odors can be a challenge, and you can have noises, particularly blower motor noise. You can have noise in the dash. So these are some of the things that I'm, might be thinking about. How do we go about? How do we address as part of our diagnosis? So, the question that we often need to answer is the problem really in the dash? The customer has all these different types of complaints: too hot, too cold, not enough airflow, and so on. And often it's important to really satisfy that the problem is actually in the HVAC case or in the dash. So just for the record here, This is a this is a kind of a simplified schematic, airflow schematic of a typical HVAC case, and you can see over here on the right hand side, over here on the right hand side, here is the air can either come in from the outside if we have the button set on fresh air, or we can draw it from inside if we have it set on recirc. And the thing to understand, the thing to note here is that if the air is coming from the outside, the first thing that's going to come through, if the vehicle has one, is the cabin airflow filter. And so, of course, here's the recirc door. If it's swung over here, it's going to be coming from inside. It's going to be on recirc. If the door is closed over here against this side, it'll be drawing fresh air in through the cabin air filter. Now, of course, as we can see here, the blow motor is downstream of the cabin air filter. We're going to look at a case study in a moment where this is actually comes into play, and then the air is forced through the evaporator. Now, what I want you to note here, that regardless of whether it's winter, summer, at all times, the airflow entering the case, when it all the airflow, whether we are on air conditioning or heating, all the air actually entering this cabin must come through the evaporator. And that's why even when we're only using heat, for example, if there's a restriction in the evaporator, like debris or something on the evaporator, it's going to restrict airflow volume. So that's important to keep in mind, that even if the complaint is in wintertime and the airflow feels like it's low, a clogged evaporator will restrict air under any circumstances. The other important thing to point out here is, remember, in the wintertime, when you put the system on defrost or defog, to defrost or defog the windshield, typically the compressor is going to run. If it's above freezing, the compressor will run. So we chill the air first, and then we will pass it through the heater core and up through to the windshield to defog or de-ice the windshield. So that's there are a couple of important things to keep in mind here. Is for defog or defrost to work, the air conditioning has to work, and that can be a common complaint in the wintertime. The air coming out the vent feels pretty hot, but it's still not as effective as it used to be at defogging or de-icing the windshield, and that may be because the compressor, the AC, is not running as it should in cold weather in defrost mode. Things I would also generally point out here is that, when you're installing an evaporator, when you're installing a heater core, it's very important that there be a full, snug fit in the case that air can't bypass around the motor. And as we'll point it out in a later slide, but it's easier maybe to explain here, the doors, the air doors, they must seal. If you have the HVAC case out, often it can be 7, 8, 9, 10, 11 hours labor to take some cases out and apart. It's important that if there's degraded rubber or foam insulation, no sense in putting it back like that. Otherwise, you're going to have internal air leaks bypassing either the evaporator or the heater core or one of the doors, and your customer complaint, it's not cold enough, it's not hot enough, the air is not coming out here when it should be coming out of there. So again, this is just a quick review, just kind of a quick overview of how the air moves through the HVAC case. So simple checks, a visual check just under the hood and under the dash. A visual check is always an important piece of the puzzle. Diagnostic trouble codes. If I plug in a scan tool, do I have any kind of AC related type trouble codes? And particularly in this conversation, we're going to be looking for possible air door actuator type trouble codes. Again, we're talking internal dash airflow here. There's a lot of components in the dash: the heater core, the evaporator, the blow motor itself, the blow motor resistor, all the different actuators. The complaints relating to internal airflow could be potentially traced back to one or maybe even more of these components, and even other issues as well. So this is a very, we're not going to get too deep in the weeds here, but this is a very quick check that I like to do if the customer complaint is that the air conditioning, for example, that the duct air is not cold enough. If you take a dual channel temperature probe like we're showing here, I can clamp one probe around the evaporator outlet, the suction line where it's coming out of the firewall, and the other probe I'm going to put in the center duct. And of course, if the suction line is 44 degrees, but the duct air is 60 degrees or 65 degrees, then I know that the problem is in the dash. We know that the refrigerant coming out, returning to the compressor, is cold enough, but somehow the air that's coming out the duct is not making contact or proper contact with the ice cold evaporator. So therefore I would know that I've got a problem in the dash. I've got air bypassing probably, or maybe a blend door issue or something of that nature. On the other hand, if the suction line going back to the compressor is 65 degrees and the duct air is 70 degrees, then the problem is probably most likely a basic refrigeration circuit problem. The evaporator is simply not getting cold enough, low on charge, or some other weak compressor, some other type of basic refrigeration circuit issue. There are two caveats to that. Is if the recirc door is not blocking outside air on a hot summer day, or you have a blend door issue where heat off the heater is getting mixed in with the air-conditioned air, that can put additional stress on the evaporator, which could cause your evaporator outlet temperature to be higher than it should be, even though there's not a problem with the refrigeration system itself. The problem would still be in the dash there. So again, just going back to the schematic diagram we had at the beginning, this is a Ford F-1 2011 Ford F-150 case with the top half taken off, just showing you the airflow through here and showing you how all the air, whether it's winter or summer, all the air comes through the evaporator, and that it's important that the air doors, the rubbers and foams on air doors, that they make a firm seal, and that foam and rubber on the evaporator core and the heater core are making good contact, providing a proper seal. If the complaint is that, on air conditioning, when you're on max air, if the complaint is the air conditioning is not cold enough, one of the problems, remember, most modern systems use what we call a constant flow heater core, meaning there's no water valve to shut hot coolant circulating through the heater core. So there is always hot coolant through the heater core. So what I recommend, to cut to the chase there, if possible, while the engine is still cold, while the system is still cold, introduce a bypass hose or crimp off the coolant flow through the heater core, bring the vehicle up to working temperature, turn on the air conditioning. If it's ice cold now, if it's a constant flow heater core system that doesn't use a heater valve and it's ice cold when you block coolant flow through the heater core, you probably have a blend door problem. Either the door is not moving properly or the foam seals that we discussed are not sealing properly. The actuator is not actuator travel problem or a sealing problem. So let's take a quick look here at some blow motor and cabin air filter service tips. Many, probably 70-80% of vehicles today are now using, cabin air filters. Whereas 20 years ago, most vehicles didn't use a cabin air filter. So it's important. I think most people are accustomed to this now, but it is important to keep that in mind, not to overlook it. Should be one of your first checks when you start investigating, air conditioning or heating complaint. So I wanted to just, tying this in with cabin air filter and cabin air flow, just very quickly want to touch on brushless blow motors very quickly. Of course, the whole advantage of brushless blow motors, they're much quieter, more efficient. You can usually make them in a smaller package, which is convenient for fitting them into smaller vehicles and tight under-dash areas. And this is how they work. It's almost like an alternator in reverse. You see it's got three phase windings here, and by powering and grounding, by electronically controlling the power and the grounding of each of these windings, we can essentially make the magnetic field rotate around a series of magnets, and we can create a rotating force, a magnetic rotating force. So, recently, just FYI, we were looking at it's a Tesla, and of course it uses a brushless blow motor technology. And in the red box there, you can see that it's talking about the HVAC case the HVAC filter being at 39%, and that's important. That is an actual value, it's providing an actual readout, if you like, of how clogged or restricted, that the cabin air filter is significantly restricted, is what this value is saying. And in fact, there's a diagnostic routine that you can run, and you can see that the readout here is it failed the performance test because the computer calculates that the motor it's taking less torque to turn the blow motor, which would be typical if the air filter was clogged and the blower motor can't put enough air through. The blower motor kind of cavitates, and it actually turns faster than it needs to, or normally would, with less effort. And so that's how it's failing this test. And this is up close. This is what the actual error message read. It failed this AC performance test. And when we checked, it's pretty obvious from looking at these pictures here, the blow motor, the cabin air filter, very significantly clogged. With the new cabin air filter installed, now the test passes. And I should also just point out here in the red box there, you can actually read blow motor, the actual blow motor speed in the center stack on this Tesla. And so while this is a Tesla, very late to all the newest technology and so on and so forth, many manufacturers, even in conventional ICE and hybrid type vehicles, many manufacturers that are using brushless blow motors are using that more sophisticated electronics to make judgments, for example, about clogged air filters and so on and so forth. So quick tech tip: if you are replacing a cabin air filter, if it's possible, sometimes it's very easy to pop out the blow motor, just pull a screw and pop it out. And the reason we suggest that is if there's leaves or debris on top of the blower of the cabin filter, it prevents the debris from falling down into the blow motor into the squirrel cage, into the blow motor wheel. Because when the debris falls into the wheel, it can get stuck there, and now you can't get it out. And when you replace the filter and start it back up again, the leaves are bouncing around inside the dash. Moving air, as I think we demonstrated in our live segment there, is hard work. So a typical blower motor on full speed can pull 350 watts. So a failing blower motor typically takes out the blow motor resistor. That's the most common cause of repeat blow motor resistor failure. And that's what we're looking at in this table here. Just shows that the blower resistor is, at the lower speeds 1 and 2, the blower motor resistor is actually doing the lion's share of the work in the circuit. And in fact, in this picture here, you can see that the resistor block is at 536 degrees. So it's significant stress on the blower resistor. And this is why, that's why we, remember during our introduction, we talked about burned terminals and so on. That's what is the most typical cause of blown resistors and blown connectors and burned connectors, is a failing blow motor drawing too much current. So this is just an example of a blow motor pulling 27 amps, which is almost 400 watts. And, you're going to have repeat and rapid blow motor resistor failure if you keep putting new resistors into the same vehicle with this blow motor. So oftentimes the fix, that's why for popular vehicles with high pattern failures, we typically make the resistor, a high temp blower pigtail, and the blow motor available as a kit assembly. A quick tip here, this is 08, I think, to 012. Ford Escapes, you can get repeat blow motor resistor failure, and the customer may also complain that the air conditioning barely works at all. When the technician checks it out, high side pressure is usually 350 psi, give or take, and nothing obvious being found. The shop recovers and recharges the system. It works okay for a while, and it comes back with the same symptom in a week or so later. And the cut to the chase here is this: the cause of this problem is the very lowest speed of the blower motor resistor fails. So the blower motor doesn't blow at all, but the compressor, the AC, continues to work. The compressor continues to work. And with the blower motor resistor failed on low speed, there is zero, there's virtually no heat load on the evaporator, and so the evaporator gets ice cold, and the low side of the system drops into a vacuum, and it draws air in through past the front seal of the compressor, especially on older models. And so this is how air gets in the system. That's why the pressure goes to 350 psi. And so a failed blower motor resistor can be the cause of this repeat air conditioning performance concern. So as I mentioned, we have a live demonstration set up in the shop here today. So let's go to, I've got a couple of demonstration boards set up. Let's go to those, and we'll take a look at how we can use an oscilloscope and a current probe to get some deep insights into blower motor performance and blower motor failure issues. Okay, so today we have a couple of demonstration boards set up, and we're going to use them to take a quick look, use an oscilloscope to get some diagnostic insights into different blower motor circuit issues. If you look here, I've got a brushless type blower motor. This, of course, is the latest technology. You find it in many modern vehicles now. Over here, I've got it's a pulse width modulated signal generator, and it's inexpensive, $20, $30 online. I found I can adjust both the frequency and the duty cycle, and that's important because I use it for testing brushless blower motors, and you can use it for different vehicle control type testing. But the advantage of being able to manipulate both is that different manufacturers use different frequencies and different duty cycle profiles to control the motor. So having a signal generator where you can control both, you can configure it to test any brushless type blower motors. That's a brushless type blower motor here. Over here you can see I've got a current probe. I don't know whether you can see it completely here. I've got a current probe on one of the main wires going to the blower motor, and this way we'll be able to look at the digital signal coming from the HVAC module, if you like, to the blower motor control electronics, and we'll be able to look at the current in the circuit at the same time. Now over here I've got a conventional brush type blower motor, two of them, and this is perfectly normal, nothing wrong with it here. And as we shall see, this is a motor here with an actual issue. Now in the middle here, you can see I've actually got a blower motor, conventional blower motor resistor. I've also, you may not be able to see it on the camera, I've got a blower motor switch so I can control the speed of the blower motor. And I've also got a thermal camera, so we'll be able to look. You can probably see it here. The resistor was running previously, so it's a little bit warm. We'll be able to look at the effect on the blower motor resistor. When there are different issues in the circuit, we'll see what kind of an effect that has on the blower motor resistor. On the excuse me. On this blower motor board, on this demonstration board here, I've got 4 blower motors, and one of them is going to be pretty normal. And these other 3 motors here have a particular type of issue. Now, I don't have any resistors or speed controls. These are just going to be connected directly to battery positive, so we'll see them run at full speed. And we're going to use some wave patterns, current wave patterns, to get some insights into what might be going on with some of these blower motors. Now, you'll note that I've got 2 identical current probes on the same wire, and the reason for that is, in the interest of time, I mean, you could do this at your shop, but you can get the same job done with just 1 probe. But in the interest of time here, I'm going to look at one of these current probes in AC coupled mode, and we'll look at the other probe in DC coupled mode, and we'll be able to look at 2 different characteristics of each wave pattern with these 2 current probes. So going back to our brushless blower motor here, we're going to go ahead and take a quick look at some of the current patterns here, and I've already got my scope set up, and you can see that right now you can see that the pattern is actually we'll just turn it live. There it's live, and you can see that the duty cycle is about 90%, give or take right now. That's the blue pattern, and the red pattern down the bottom there, that's actually our current probe. right? So what we are going to do is I'm going to adjust this duty cycle here from about 90% all the way down to 30%. And as I do that, you should see the duty cycle change on top. And of course, the current, more and more current should start flowing in the motor. So you can see the duty cycle, the negative duty cycle, the time that the circuit is low, increase in the blue pattern. And you can see the current coming up in the red pattern. So if you were doing this, so again, this is how you could test a brushless blow motor on many different vehicles with a simple current probe and voltage channel hookup. And you can see the current flow is increasing. And now I overshot a little bit. Let me just go back to 30%, which should be about full maximum speed. And you can see the duty cycle on top there is about, the pattern actually represents about 30%. And if I pull a cursor down here, red cursor down, on the average we're probably about 22, 23 amps. So that's, again, that's how we could use an oscilloscope to check a brushless blow motor. Now, the one thing that's missing here that you may find on many modern vehicles is often there will be a digital feedback signal from the motor back to the control module, the speed control module, confirming that the motor has, is achieving the requested speeds. And again, you would just look at that signal. It's usually digital square wave, or it'll be a changing analog signal. I've seen some Chryslers with a changing analog signal. Either way, you'll be able to look at that signal, the feedback signal, with another channel on your scope. So over here, of course, we have two blow motors. As I said, one has a problem, the other is perfectly normal. And we're going to go ahead and we're going to power them up with this setup here. And you can see, here I am, there's my temperature probe. And what I want you to notice here is this. The other thing we're also going to do, we're going to look at the current. We're going to look at the current for this, for the good and the bad blow motor. And we're going to see the impact on blow motor current and on the resistor temperature with a good and bad motor in the circuit. So let me just open up my test pattern here. And let's go live with our scope. And there you see the two patterns is live. So the red pattern represents current or amps. I will just change the, we're just going to look at it, we're not going to do a big look at it. We're just going to look at it under a couple of different circumstances here. And we're going to move this probe of our scope over here to the voltage. So the blue channel will represent the voltage at the motor, and the red channel is the current flowing in the circuit. And I'm going to start with the good motor. So I'm going to go ahead and plug in the good blow motor. And we're going to just run it on the low speed, on the lowest speed of the resistor, like this here. And you can see, I can't see it exactly, it's quite difficult to see. It's probably around 160, 170 degrees on the resistor. Again, we just plugged it in. It usually gets warmer. And if we go back now and look at our oscilloscope, we can see, I'll just pull a cursor down, you can see that the current flowing in the blow motor circuit right now is about just about 2.5 amps, right? So what I'm going to do is this blow motor on the right, this blow motor here that we looked at before, this blow motor here on the right, actually has a problem. So I'm just going to switch my power supply from the good motor to the bad motor, and we're going to look at the impact on current and on the blow motor resistor temperature. And the first thing, if we go back to, if we just look at this motor again for a moment, you can actually see that it's moving by a tiny amount. It is actually moving, right? Just barely. But if we go back and look at our current and pull a cursor down, you can see that even though the motor is not moving or just barely moving, it's actually pulling about an amp more, 3.2 amps just about. It's pulling almost an amp more current than the good motor, even though it's not moving. Now, so if I crank up, if I go to the second speed, maybe even the third speed. Notice now, if we look at the motor, you can hear it's noisy. This motor's actually got a bad bearing, and you can hear that it's noisy, but it does work. So I'm going to shut it off here for a minute. So here's a classic example. Here's why it's so important to, more than likely, if you have a failed blower resistor, you probably have a failed or failing blower motor. And this is a classic example here, is whereas this motor does run at the higher speeds, but if the customer was to leave the motor at speeds 1 or 2, it would continue to draw current, but wouldn't actually be running. And of course, when the motor is not blowing, the resistor gets even hotter still because there's no airflow across it. And so that's how a defective or a failing blower motor results in repeat blower motor failure, or blower motor resistor failure, and often, of course, as well, burns out the pigtail. So with that, we're going to go back to our other board and look at some of the circumstances on, let's look at some of the setups on that board. So the first one we're going to look at is this motor here. This should be a pretty normal pattern. Again, we're going to look at all these motors at high speed, at normal speed. I do have some presets to save time here. I've got some presets set up. So we're going to go ahead and open this. So this is blower number 1, which should be pretty normal. And what I want you to, so I've opened it up static here. So I'm going to explain very quickly what we're looking at here. The other thing I want to point out here is, even if you don't have a current probe, if you have an oscilloscope, a simple, straightforward oscilloscope, and you put it on the blower motor power supply, let's say, and you set the scope, you AC couple the scope. This way we will only look at the changing voltage component of the signal. And on channel A, that's what we've got. We've got channel A set on volts, but it's AC coupled plus or minus a half a volt, 500 millivolts, right? On channel B, which is the red channel, that is a current probe, and it is also set on it's AC coupled on amps, on current, and it's showing us we're just looking at the changing, the top of the froth, if you like, the very top of the waveform, the changing part of the waveform. And then on channel C, which is the green channel, we are looking at the regular current, right? And so if you look at channel, if I pull a green cursor down here, this motor is pulling approximately 10 amps, as you can see. Now note that while the voltage that channel A, which is set on voltage, it's not giving us an absolute current value, but it is showing us a pattern that you can see very closely. If we move it up a little bit, you can see that it's kind of a mirror image. It's a reflection of the current pattern. So again, as you will see in a moment when we look at a bad motor, you could just use a simple single voltage probe, AC coupled, to see issues in blower motor, in fact, in any kind of rotating electric circuit. Now looking at the channel B, which is a red channel, we're only looking at the AC component of the signal here. And I'm going to pull out a couple of cursors, and I'm sure you can see by looking at it already that there's a repeating, the very obvious repeating component of this pattern. So if I go from here to about here, you can see that, there's a very rhythmic repeating pattern here, and it's taking, actually, if I look at my panel up above here, it's taking about 9 milliseconds for this motor to go through one full revolution, right? Because that repeating pattern, that's what's telling me the brushes are worn in a very particular way, the segments of the rotor are worn in a particular way. We can usually easily pick out one rotation of the motor. And in fact, this picoscope is doing the math for us. This motor is turning at high speed, it's turning at about 6,600 RPM. Now, just doing the math, the scope is making it easy for us here, but if you didn't have this calculation, remember there are 60,000 milliseconds in a second. If you were to divide 9 milliseconds into 60,000, that should give you the same number here, 6,687 RPM, right? So that's what's going on. So now let's look at some problem patterns here. So I've got them, and so that you can see that this is actually a real pattern. I'm going to go live for a moment. And I'm going to go ahead and I'm just going to connect up that blow motor so you will actually see in real time what the signal looks like. And again, this is the pattern that we were just looking at. So now I'm going to go ahead and open up. I've got it all set up already. So I'm going to open up the next, the number 2 motor. Going to open up the number 2 motor. And of course I've got to switch to that motor. Now you may be able to hear in the background it's making a little bit of noise. The bearing is definitely making a little bit of noise. And looking at the pattern, especially when you look at the AC coupled current pattern, the red pattern on the bottom, you can see pretty quickly that there's definitely a developing problem in this motor. Compared to the smooth pattern we saw on the original new perfect motor, you can see there's definitely, I can hear it here. I don't know whether you can hear it over the microphone or not, but I can certainly hear it here. There is a developing problem with this motor. So now I am going to, let me just pause that. I will shut this motor off for a moment. And then we're going to move on to our 3rd motor, right? And I've actually, I have got a scope pattern. I've got a template for that all set up already, so we don't have to adjust our scope on the fly. It's going to be number 3. And then I'm going to go live. And I think you can see here pretty quickly, this has a dead segment, at least one dead segment in the rotor of this blow motor. Now the thing to keep in mind is this motor is turning. You can probably hear it in the background. I think we can switch to that camera and take a look at it. You can see that this motor is actually turning. Now if I do the math we did before for how long it's taken to go through one full revolution, I think we would find that it's turning a lot slower than the new motor we looked at a moment ago. But looking at our current pattern here, I think it's pretty obvious. It doesn't take a rocket scientist to figure out that there's a very definite problem with this, with the pattern here. So let me just go live again. And there you can see, I've got an obvious, you can see like right here, in this section right here, the current goes to 0. That means there's a flat or a dead, the segment is probably burned or worn, or the winding could be open. This is the classic motor where the customer complaints is it intermittently shuts off, or when I turn it on, it doesn't start up until I go over a bump or something of that nature. This is the classic intermittent blow motor operation scenario. And of course, oftentimes it might only happen once every day or 2 days or a couple of days, and you might be thinking it's a connection problem or something of that nature. Looking at the blow motor circuit with the current probe can give you deep insight into what's going on with the circuit. So let me just shut this motor off for one moment, and we will now quickly move over to motor number 4. And I'm going to pull up the template for that first. And then we're going to go live on the circuit. I will actually connect this motor up and make it run. Hopefully you can hear it. And I'm going to go live on the scope. And here we have, now you can see, here's another classic blow motor current pattern. I'm going to pause it so we can talk about it and analyze it. I will shut the motor off so we can hear a little better and talk about the pattern. And again, the top pattern here, if I look at the green, that is DC coupled. It's on a 20 amp scale. This motor, that's just the straightforward current for this motor. And on the average, it's open, it's an open air here. It's not pulling a lot of current. It's pulling about 9 amps. I mean, blow motors, in the case could be pulling 15 to 25 amps would be pretty common on a lot of motors when they're actually in the case forcing air through the system, drawing it through the filter and pushing it through the system. Here it's just running in the wide open. The blue pattern, again, it's just a simple voltage plus or minus 500 millivolts, plus or minus half a volt. And you can see that the blue pattern, the point I'm making about the blue pattern is that you could take a simple voltage probe from your scope, put the AC couplet like you can see here, and you would be able to get a very similar sense of a brush problem in the circuit with the simple, even if you didn't have a current probe. Now, if we look at the red pattern, which of course the red pattern is current again, but this time the current is AC coupled, so we're just looking at the changing component of the signal. And here I think I'm actually going to move the green and the blue out of the way and just focus on the red pattern for one moment. And I think you can see here, it doesn't look too bad, but there's a very obvious, you can pretty much see here, there's a very obvious issue with this. Now the motor runs fine, it doesn't make any odd noises at all, so I put it here and put my here. It's running about 5,200 RPM. A lot of these motors at high speed, a typical brush type motor will run, 5, 6, 7,000 RPM. And I think you can see here, it's running at the proper speed. It's not making any noise, but there's a very obvious, there's probably a segment here that's worn, right here. We're getting right here, looking like we have a worn segment. We get a little amperage spike right after, on the segment right after the worn or the worn one. And so the point I'm making with this pattern is, here's a blower motor. Maybe I've just replaced the blower motor resistor. The customer takes the vehicle. This is the kind of vehicle that's going to turn up back in my shop in 2-3 months down the road with a failed blower motor, and possibly, depending on how it fails, a possible burned blower motor resistor or blower motor resistor pigtail or connector. So that's using a current probe to get insights into problems or issues with different types of blower motors. So let's go back to our presentation and take it away. So here is a quick airflow case study. It's a 2013 Hyundai Sonata, 25,000, very low miles, 25,000 miles. And the customer says that the air conditioning is not as cold as it used to be. And the airflow from the ducts, from the dash, feels weak. They say it's not as strong as it used to be. And so, of course, looking at the cabin air filter, it is clogged. And we discussed before, if you can, drop the motor so you don't let leaves fall into the motor. That's a quick tip from previously. The technician of the shop replaced the cabin air filter, and it's improved. If we look at the duct temperature here, the performance of the system is improved, but the customer says it's still not quite as good as it was previously, right? Make a long story short here, that the technician used an anemometer, which is a little device that it's got a propeller there. You can see it in the right hand over the duct, and it will measure airflow. And when he checks, it's about 1,059 feet per minute. Of course, he doesn't have a spec for this, but he's got some experience using this tool. And on a hunch, so he checks the airflow, it's about 1,000 feet per minute. And on a hunch, he checks it. He also, like we did with our dual channel probes previously, he sets up his current probes to check AC current and DC current on a scope. And, from that he measures, like we discussed previously, he can measure blower motor RPM. And with the different filter, he finds that the blower motor is turning significantly faster than it did before. And so with the different filter in there, you can see now where it was 1,000 feet per minute before, now it's up about 1,600 feet per minute. And the point I'm making here is that I have seen replacement filters that can be quite expensive, the material and the design of the filter is important. The filter on the right here was actually, that's the filter that was restricting the airflow. That filter was causing a significant reduction, a restriction in the airflow. And that's what was causing the customers, they still weren't happy with the airflow even after the filter had been replaced. So air door actuators, again, you got your defrost actuator, the panel or mode door actuator, and they're typically when you're calling the parts door, they're usually called the blend door, the recirc door, and the mode door, the typical names for these actuators. So there are two wires very simple, almost like a power window motor, simple 2-wire motor without feedback. The control module can just reverse the polarity to drive the actuator in either direction. This is the type of setup often used in some older vehicles, especially to drive the recirc door would be a very common application for this type of circuit. Now, here we have 2-wire with feedback. And so, again, it's just bidirectional. The power one side and ground the other. The motor is going to turn in one direction, reverse the polarity, the motor will move and turn in the opposite direction. The difference here is that the little pulses, a bit like we were looking at on our blower motor demonstration earlier, the computer can see the pulses in the current pattern, and it uses that information to actually count the rotations of the motor, like we were doing in our live demonstration of the blower motor. The computer can use this information to keep track of the actual position of the air door actuator. So this is what we would call 2-wire with feedback. Now we can have an actuator with position feedback. Here there is a little bit of electronics as part of the actuator assembly, and the circuit there that says actuator control, the computer can just change the voltage on that circuit. 5 volts, the motor will turn in one direction. 0 volts, the motor will turn the opposite direction. If I just put 2.5 volts in that circuit, the motor will hold at whatever position it happens to be at. And the other 3 wires, ground, signal, and 5-volt reference, just like a TPS, the computer keeps actual physical track of the actuator with that information there. So you can, if like we did earlier, you can use an oscilloscope, just like you were sweeping a TPS, to check for an intermittent glitch on an air door actuator circuit that has position feedback like we saw on the last slide. So if you have to replace it, remove the dash to replace an actuator, I just suggest review or at least contemplate if another actuator were to fail, would you have to take the dash out again? For a lot of popular vehicles, for example, we have kits. We make full, maybe a 4 actuator per kit available, so that you can just replace all the actuators in one repair. Certainly, I'm going to replace those. Any actuator that if I have to would have to take the case back out again. If another actuator were to fail, then I'm going to replace at least all those actuators that would require case removal if I have to take the case out for any reason. Now, don't forget, never turn the key on until you have the actuator actually mounted on the case. Because if you turn the key on, the computer may try to recalibrate maybe move it through its full range of travel. If there's no resistance, the motor can often go off the end of its travel, and it will actually damage the motor inside. Referenced this a little bit previously, the foam seals, rubber seals on the air doors themselves and inside the case generally, on the blower motor, on the HVAC, on the heater core and the evaporator core. It's very important that you've got good airflow integrity inside the HVAC case. This is an older GM technical service bulletin. It was issued because of repeat air door over travel trouble codes. The reason I'm referencing it here is what the calibration does is, first of all, it loosens up the counts, the actual versus the commanded position of the air doors, so it's not as strict. It doesn't set as trouble code. It allows for a little bit more slack, a bigger discrepancy between the actual position, the commanded position of the air door. But the other thing I wanted to reference, look on the bottom where it says crush time. It's been reduced from 2 seconds to 0.4 of a second. And that is typically, and we'll see it here in this scope pattern, do you see where it says crush time 4.5 seconds? Well, that means that during an actuator, a recalibration, the computer will drive the motor to the end of its travel, and it will keep torquing it for 4.5 seconds. And then you see on the other side, it's the crush time is actually 12 seconds or 12.5 seconds. And so this is why the GM reduced the crush time, because as the vehicle ages, the foam collapses or condenses, and so it doesn't take as much time to seal the door against the stop. So they reduce the crush time to try to prevent the system from setting over travel trouble codes. And that's another reason for performing. I often would perform an air door recalibration procedure as part of my diagnostic routine, because during the recalibration, the computer will drive each air door through the full extent, to the open and close to the maximum extent of its travel in either direction, and that can often reveal, it will often set a trouble code or reveal a problem with a particular air door actuator, especially if the problem is intermittent. And in fact, here's a GM, 94 to 2014 GM vehicles. They used a plastic gear with the center, metal center, and the gears are notorious for cracking. And so they often will cause intermittent diagnostic trouble codes. And one way to really shake them out or flush them out is to perform a recalibration procedure and check for trouble codes. So some HVAC case service tips. 09 and later F-150s, they're notorious for, they don't use a cabin air filter, and they're notorious, particularly in rough environments, dusty environments, the evaporator can completely cover it over and create significant airflow restriction. Now, a quick way to get one quick tip to get a handle on this is to compare evaporator target temperature with compare evaporator target temperature with our actual temperature. If they're both low and close, you can see here 36 and 37 degrees, but the duct temperature is maybe 10, 15 degrees higher than that, that tells me the evaporator is ice cold. It's cold enough to get the job done, but the air coming out the duct is not cold enough, probably bypassing the evaporator core because the evaporator core is restricted. So this is a quick check or a quick tip to get you pointed in the right direction on those, specifically on these F-150s, but you can use the technique in any vehicle that you're working on. A big discussion comes up. Oftentimes, if you go to the Ford dealership, you will replace a heater core or an evaporator core. You may have to buy the entire HVAC case. So if I'm going into the case to replace the evaporator core, for example, which is the most effective repair for this airflow restriction that I'm talking about, again, it's not pretty in there. Look, I'm not recommending that you replace everything when you go in there, but I'm certainly going to have my eyes open, and depending on the mileage and the condition and so on, consider replacing any of these components that would require the case to be taken out again if any of them were to fail in the near future. So again, looking at, kind of going back to our previous tip there, looking at target temperature versus actual evaporator temperature can give you quick diagnostic direction. You can see here that the evaporator actual temperature is 62 degrees, but the target temperature is 39 degrees. So in other words, the computer wants the evaporator temperature at 39 degrees, but the actual temperature is 62. In this case here, I would suspect a basic refrigeration circuit problem. The computer is aiming for 39, 40 degree evaporator, but it can't get there, more than likely because the system is low in refrigerant, or there's some compressor issue. There's a basic refrigeration system problem, more than likely, on this vehicle. So the heater system, again, these are just very quick tips here. On a hot working vehicle, I'd expect the heater core inlet temperature to be about 195 degrees plus. Usually on a good working heater system with the blower on high, you're going to see a 30, 40 degree temperature drop from the inlet to the outlet. A good rough rule of thumb for duct air should be maybe 135 or 140 degrees or warmer coming out the ducts with the system set on max heat. If you see a large temperature drop across the heater core, there's probably no flow. There's hot coolant going right up to it, but there's nothing coming through it, and that would usually indicate a clogged heater core. If it's a small drop, limited flow, there's some flow going through there, but there's a lot of clogged passages, and so there's very little heat absorption. That's why you're not getting a very big temperature drop across the heater core. So here's what we talked about today. Is it an airflow problem? I think we kind of answered that with a quick tip at the very beginning. We looked at blower motor and cabin air filter service. We did some live demonstrations on the demonstration boards. We discussed air door actuators. We gave you some HVAC case service tips. And then we wrapped it up with a quick slide on the heater, kind of quick tips for heater system diagnosis and service. So before we go, don't forget we do have a temperature control tech line. It's free to call. They can help you with both technical problems. If you have an air conditioning or heater related technical concern, they can certainly provide you with some diagnostic assistance and insight that may help you there. Also, if you have a cataloging issue, an application question, you're trying to match up a part or a hard to find part, they can very often be very helpful with getting you, pairing up a part that will work for you if you're having difficulty finding a particular part. So that is our show for today. But before we close it out, I'm going to check with Corey. Corey, do we have any questions before you go?
You know what? We do have a couple. I've answered a few back here in the background, Peter, but we do have a couple that I know that are near and dear to your heart, so I'm going to bring these up for you.
Okay.
The question is, I see a lot of options for high temp pigtail replacement. Not on everything, but a lot of the stuff I'm seeing. Do I really need to upgrade to the high temp pigtail if it's an option on anything?
Okay, so here, for example, is an example of a high temperature connector. What I would say about that is usually, when we have a high temperature connection pigtail available, it's usually been made available because we have identified that particular connection, that blow motor resistor, or that particular connection as being a problem connector. In other words, we see a frequent burnout of that connector. So in those circumstances, typically if you see a high temperature pigtail available, I would highly recommend using it. The other thing to keep in mind, of course, is you almost certainly will need to replace the blower motor resistor at the same time, because as you can see here, the terminal pigtail is burned out. Well, where that plugs in on the other side into the resistor block, that terminal will also be burned. So to your question, I always recommend the high temperature connector when it's available, and of course, replace it with the blower motor resistor. They're usually available in a kit. In fact, typically today, especially for problem vehicles, for problem applications, we would have the blower motor resistor, the blower motor itself, and the pigtail all available as a kit. And the reason that we do that is because we know, we've just from experience, from feedback, we know that these are particularly high failure rate applications.
All right, I think that answers that one. And then in a spirit of time here, I'll throw one more out there. And this is a good one. So I see on some vehicles that have a brushless blower motor that there are cheaper options for brushed motors. Is that, a good thing to do? Can I get away with using those cheaper versions, or what would your take be on that?
I would be very careful choosing a brush type motor where the OE vehicle came with the brushless motor. For example, if you look up in the dash on a 2015, 2016 Chrysler application, for example, the two wires, the power and the ground going to the blower motor, are a twisted pair, and it's braided just like a TV cable. And the reason for that is because they're using a brush type motor and a pulse width modulated brush type motor, which creates a lot of noise. So generally, brush type motors create a lot of electrical noise. The brushes create a lot of electrical noise when they contact the segments. And in general, I do not recommend using a brush type motor if the vehicle came originally with the brushless motor. Brushless motors are, it's all electronic. They're very quiet. They don't generate a lot of electrical noise. Using a brush type in its place could generate electrical interference onto the dash that could interfere with the communication circuits and so on. So in general, I do not recommend using a brush type. If a brushless option is available, I would highly recommend sticking with the brushless replacement.
All right, Peter. Well, thank you for answering those for us. And with that, I'll let you take us out. And thank you for being here again.
Folks, thank you very much for spending this hour more or less with us. And see you again next month. Thank you very much.